Welcome to today's video, where we'll be diving into the top 10 unexplained mysteries in physics. From the vast reaches of the universe to the microscopic world of particles, there are still many phenomena that challenge our understanding of the laws of nature. Some of these mysteries have puzzled scientists for decades, while others are just beginning to reveal themselves. In this video, we'll explore some of the most intriguing and perplexing questions in modern physics, including the nature of dark matter, the strange behavior of time, and the very fabric of reality itself. Let's take a closer look at these unsolved mysteries that could one day change our understanding of the universe. Number 10. The Hubble tension. The Hubble constant is a fundamental value that determines the rate at which the universe is expanding. It's essential for calculating distances in cosmology, understanding the age of the universe, and mapping its overall structure. However, recent measurements of this value have produced conflicting results. Two primary methods are used to determine the Hubble constant. One relies on observations of the cosmic microwave background, CMB, from the early universe, and the other measures the distance to nearby galaxies using supernovae as standard candles. These methods should theoretically produce the same result, but they don't. This discrepancy is known as the Hubble tension. The Hubble tension suggests that there might be new physics at play, or perhaps there are unaccounted for errors in the measurements. Some theories suggest that unknown forces, or even the possibility of a change in the physics of the early universe, could explain the discrepancy. On the other hand, some physicists suspect that the issue could be due to systematic errors, such as miscalculations in the way we measure distances or interpret data from distant galaxies. If this problem is resolved, it could lead to a massive shift in our understanding of cosmology, offering insight into the true nature of the universe's expansion and its fundamental laws. Number 9. Dark matter. Dark matter is one of the most perplexing and elusive substances in the universe. While scientists cannot directly observe dark matter, they infer its existence based on its gravitational effects. Observations of galaxies and galaxy clusters show that there is far more mass present than we can account for with visible matter. Without dark matter, galaxies would not have enough mass to stay bound together, and the universe's structure would be vastly different. This missing mass is thought to make up around 27% of the universe's total mass energy content. Despite the extensive evidence for dark matter's existence, it has proven impossible to detect directly. It doesn't interact with electromagnetic radiation, meaning it doesn't emit, absorb, or reflect light, so it cannot be seen with telescopes. The leading theory suggests dark matter is made of exotic particles, such as WIMPs, weakly interacting massive particles, or axions, but so far, these particles have eluded detection. Unlocking the mystery of dark matter could provide the key to understanding the true makeup of the universe and even lead to new discoveries in fundamental physics, helping us understand forces and particles we've never observed before. Number 8. Dark energy. If dark matter is the unseen mass that holds galaxies together, dark energy is the mysterious force that is causing the universe to expand at an accelerating rate. Discovered in the late 1990s through observations of distant supernovae, dark energy now accounts for about 68% of the universe. It is thought to oppose the force of gravity, pushing galaxies away from one another rather than pulling them together. This acceleration is the reason why the universe's expansion is speeding up rather than slowing down, as had been expected based on gravitational forces. The true nature of dark energy is still unknown. Some theories suggest it may be related to vacuum energy or cosmological constant, an idea introduced by Einstein as part of his theory of general relativity. Other ideas propose that it might be a sign of modifications to our understanding of gravity on cosmic scales. Whatever its nature, dark energy is one of the most significant and puzzling forces in the universe, influencing the universe's fate. Some speculate that it could even lead to the Big Rip, a scenario in which the expansion of the universe becomes so rapid that it tears apart galaxies, stars, and eventually atoms. Number 7. The matter-antimatter asymmetry. At the dawn of the universe, the Big Bang should have produced equal amounts of matter and antimatter. However, when matter and antimatter meet, they annihilate each other in a burst of energy, meaning that if they had been created in equal amounts, the universe would have ended up as pure radiation, with no leftover matter to form stars, galaxies, or planets. And yet, we observe a universe dominated by matter, with antimatter being almost completely absent. This imbalance is known as the matter-antimatter asymmetry, and it remains one of the most profound mysteries in physics. Scientists have yet to explain why there is more matter than antimatter in the observable universe. Some hypotheses suggest that during the very early universe, processes occurred that slightly favored the production of matter over antimatter, leading to the imbalance we observe today. One possible mechanism is CP violation, charge parity symmetry violation, which could have caused this bias in the creation of matter over antimatter. Understanding the origins of this asymmetry could reveal new laws of physics and provide answers to why our universe is made of the matter we see, rather than an equal mix of matter and antimatter that would cancel out. Number 6. The strong CP problem. Quantum chromodynamics, QCD, is the theory that explains the strong force which holds atomic nuclei together. According to QCD, there should be a phenomenon known as CP violation in the strong interaction. This means that the strong force should behave differently if you reverse charge C and parity P, but no significant violation of CP symmetry has been observed in strong interactions. The absence of this expected CP violation is known as the strong CP problem. The puzzle lies in the fact that CP violation is observed in the weak force, responsible for radioactive decay, but not in the strong force. Some theories, like the axion theory, propose that new particles might resolve this discrepancy. If such particles exist, they could help explain not only the strong CP problem, but also other cosmic mysteries, such as the matter-antimatter asymmetry. Understanding this puzzle could reveal new aspects of fundamental physics and deepen our understanding of the universe's forces. Number 5. The measurement problem in quantum mechanics. In the strange world of quantum mechanics, particles can exist in a superposition of states, meaning they can be in multiple positions or conditions at once. But when we measure or observe them, they collapse into a single state. This phenomenon creates the measurement problem. What exactly causes the collapse of the wave function when we observe a quantum system? This issue has baffled physicists for decades and lies at the heart of the philosophical debate surrounding the foundations of quantum mechanics. Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that observation plays a crucial role in determining the outcome of quantum events. On the other hand, the many worlds interpretation proposes that every possible outcome of a quantum event actually occurs, but in separate, non-interacting parallel universes. No matter which interpretation one favors, the core mystery remains the same. What exactly causes the wave function to collapse? Solving the measurement problem could lead to a deeper understanding of both quantum mechanics and the role of consciousness in the universe. Number 4. Quantum gravity. One of the biggest open questions in modern physics is how to reconcile general relativity, which describes the force of gravity on a large scale, and quantum mechanics, which governs the behavior of particles on the smallest scales. These two theories work brilliantly within their domains, but they are fundamentally incompatible. Quantum gravity seeks to merge the two, offering a theory that would describe gravity in quantum terms and explain how the gravitational force behaves on microscopic scales, such as inside black holes or the early universe. Several approaches have been proposed to solve this problem, including string theory, which suggests that the fundamental particles of nature are actually tiny, vibrating strings, and loop quantum gravity, which seeks to quantize space-time itself. However, no theory of quantum gravity has been proven or universally accepted yet. Finding a unified theory could not only resolve inconsistencies in current physics, but could also unlock answers to some of the most extreme phenomena in the universe, such as the nature of black holes, singularities, and the birth of the universe itself. Number 3. The chirality in molecules and the universe. Chirality refers to the property of objects being non-superimposable on their mirror images, much like our left and right hands. In the realm of molecules, chirality plays a critical role in the structure of biological molecules. For example, amino acids, which form the building blocks of proteins, are predominantly left-handed, while sugars are right-handed. Yet, the origin of this homochirality, the preference for one-handedness over the other in nature, remains unexplained. The chirality problem extends beyond biology and into the realm of fundamental physics. Some theorists propose that early chemical processes, perhaps influenced by cosmic conditions or asymmetries in fundamental forces, might have favored one chirality over another. Others think it could be tied to quantum physics or even fundamental particles, like neutrinos, which exhibit a preferred chirality in their interactions. Uncovering why nature favors one chirality could not only explain the origins of life on Earth, but also lead to breakthroughs in our understanding of the fundamental laws of nature and the structure of the universe. Number 2. The nature of time. Time is something we all experience, but it remains one of the most mysterious concepts in physics. We all perceive time as flowing from the past, through the present, and into the future. Yet, the laws of physics are largely time-symmetric, meaning they don't inherently distinguish between past and future. For instance, in classical mechanics, if you reverse the direction of time, the equations of motion would still hold true. So, what causes time to flow in one direction? This is known as the arrow of time problem. The most widely accepted explanation is tied to the second law of thermodynamics, which states that entropy, the measure of disorder, always increases over time. In other words, time flows in one direction because the universe is constantly becoming more disordered. However, this explanation doesn't fully account for why time itself should have an inherent direction. Some physicists argue that the origin of time's flow could be linked to the Big Bang or to quantum mechanics in ways we don't yet understand. Understanding the true nature of time could lead to a groundbreaking shift in our view of the universe and help us unlock deeper questions about the laws of nature. Number 1. The origin of life. The origin of life is one of the greatest mysteries, not just in physics, but in all of science. How did non-living molecules come together to form the first living organisms on Earth? This question has fascinated scientists for centuries, and while there are many theories, a definitive answer remains elusive. The most popular idea is that life began in a primordial soup where organic molecules formed under the right chemical and environmental conditions. These molecules may have combined to form self-replicating structures, eventually leading to the complex cells that make up all living organisms today. But what sparked this process? Was it lightning strikes, deep-sea hydrothermal vents, or even molecules delivered to Earth by comets or meteorites? And how did these molecules overcome the immense improbabilities of forming complex systems like DNA, RNA, and proteins? Some researchers look to physics for answers, exploring how the fundamental laws of energy and entropy could have played a role in organizing matter into life. Solving this mystery could not only reveal the secrets of our own origins, but also guide the search for life on other planets, offering a deeper understanding of what it means to be alive. Thank you for watching, and as always, like, subscribe, and share this video for more upcoming coverage of this amazing, wondrous universe we live in.